You crack open a typical hard-boiled egg and find a thick, gray-green ring tightly hugging the yolk. While it looks like rot, there is no biological decay happening here. This discoloration is a precise inorganic compound called iron sulfide. It is the exact same chemical reaction that causes silver jewelry to turn black. By treating the egg as a sealed chemical reactor, we can map its thermal thresholds and prevent this compound from forming. The egg interior consists of two biochemically stable zones, separated by a thin physical membrane. In the yolk, we find our first reactant. Roughly 95% of the egg's iron is stored here, but that iron is locked inside a protein called phosvitin, which maintains a secure grip on the iron atoms. Across the membrane, the egg white holds our second reactant. Cysteine proteins carry sulfur atoms, neutralized and bound to hydrogen. At standard temperatures, these molecules lack the energy to break their bonds. The iron and the sulfur sit inches apart, entirely static. They remain isolated from each other unless a specific external catalyst forces the proteins to unfold. The green ring is a symptom of thermodynamic user error rather than an inherent biological flaw of the egg. Boiling water provides the thermal energy that destabilizes this internal reactor. The disruption begins as the internal temperature crosses 70 degrees Celsius. This thermometer shows the 70-degree threshold. As the white heats up, the cysteine proteins unfold and the sulfur-hydrogen bonds physically snap apart. This fracture releases volatile hydrogen sulfide gas. Pressure inside the white begins to build. Simultaneously, a parallel thermal breakdown occurs on the other side of the membrane. The heat triggers a saponification of the phosphoric esters at the serine amino acids inside the yolk's phosvitin. The molecular locks break. Free ferrous iron drops out of the protein chain and floats into the yolk. The reactor is now primed, with pressurized gas on one side and free iron on the other. Crossing 70 degrees shifts the internal chemistry. The white begins generating gas, while the yolk releases the iron necessary for synthesis. Because the eggshell is sealed, the expanding hydrogen sulfide gas has no external exit. It is forced to diffuse horizontally, pushing inward toward the yolk. It travels until it reaches the membrane and meets the free iron atoms. As the crust forms, the gas and the iron react instantly. They fuse into solid, insoluble iron sulfide. How much of this compound forms depends on the thermodynamic input. There is a massive difference between a rolling boil at 100 degrees Celsius and a gentle simmer at 82 degrees. At 82 degrees, gas diffusion is slow. The formation of iron sulfide remains practically microscopic. But the internal environment changes if the yolk breaches 85 degrees Celsius. This graph compares the two temperatures. At 82 degrees, the reaction curve is flat. But at 85 degrees, the iron-sulfur reaction accelerates exponentially, creating a thick, visible crust in seconds. A 100-degree rolling boil pushes heat through the shell faster than the proteins can absorb it, triggering that 85-degree exponential reaction. Applied heat is the primary driver, but internal water chemistry presents a secondary variable. As an egg sits in storage, carbon dioxide slowly escapes through microscopic pores in the shell. The loss of carbon dioxide causes the internal pH to rise, turning the environment inside the egg significantly more alkaline. This alkalinity acts as a direct catalyst, accelerating the release of hydrogen sulfide from the cysteine proteins, even at lower temperatures. Older eggs require lower heat or shorter processing times because of this shifting molecular baseline. We can optimize the heat transfer protocol to prevent the ring. Initiate a 100-degree boil for rapid thermal penetration, then immediately eliminate the heat source. Capping the vessel allows the residual, dropping heat of the water to firm the yolk without ever breaching the 85-degree threshold. The process fails if you allow the egg to cool slowly in ambient air. The synthesis continues to run off internal residual heat unless it is aggressively decelerated in an ice bath. This chart shows the thermodynamics of the plunge. The ice water crashes the internal temperature down through the 70-degree baseline in roughly 60 seconds. This provides an immediate molecular halt. Hydrogen sulfide gas production ceases, and free iron mobility freezes. This instantaneous termination locks the reaction at a microscopic level, preventing any visual manifestation of the ring. The ice bath provides the thermodynamic break to stop the synthesis before the discoloration becomes visible. This specific affinity between sulfur and metals dictates chemical reactions across the entire professional kitchen. Cooking sulfur-rich cauliflower in a cast-iron skillet results in a dingy gray appearance because of the exact same iron sulfide synthesis. We see a closely related atomic application in the traditional use of heavy copper bowls for whipping egg white meringue. The surface copper reacts directly with the sulfur inside the egg white cysteine. This specific metal-sulfur bond pulls the proteins into a tightly stabilized network, preventing the foam from collapsing. The rules of atomic attraction are consistent. Metal grabs sulfur. Once you understand the mechanism, the behavior of ingredients becomes predictable. Mastering the culinary arts means seeing past the raw ingredients to manipulate the underlying chemical reactor. Approach your next dish with that molecular precision.